Okay. Hi, good morning. Welcome. Welcome to the GRASP seminar. I'm Dan Kotichek. I'm today's faculty host. Quick reminder, all the previously recorded talks can be found on our GRASP YouTube channel and website. If you're joining via Zoom, please submit your questions at the Q&A button at the bottom of the screen. And they're going to be wrangled by our wonderful student panelists, Jason Ma and Meghna Gumadi, who will take over at the end of the talk. Please be sure, if you're in the room, please be sure to use this mic, which I'm using so imperfectly now. You'll do a better job so that the people on Zoom can hear the questions. Okay, so it's my great pleasure and honor to introduce Professor Leslie Kaelbling, the Panasonic Professor of ECS at MIT. She's also the Director of Research at the MIT Quest for Intelligence, which I didn't even know. She exacted a promise from me to be brief. So I'll be brief. I think you're a PhD in philosophy and computer science from Stanford. You worked at the SRI AI Center, which I also didn't know. I think 1991 you came to Brown, and then 1999 you came to MIT. Is that the right terminology? Right. Okay, so Leslie is she's a pioneer in the world of machine learning. She founded one of the major journals. I promised I would be brief. She's done a lot of work in decision theory, POM-DPs, that kind of stuff. I'll be brief. She's beyond the tens of thousands of papers. I think the work that she and her collaborators are doing right now on compositional methods that use learning modules thoughtfully at multiple levels of abstraction, I believe it's some of the most important work being done in robotics and if I knew AI, I would say robotics and AI these days. So Leslie, I'm done. I'm sorry, I could say a lot more. I won't. Welcome. All
right. Okay, so thanks so much for inviting me and for the brief introduction. It's awesome. So I am going to talk about robots and learning in the modern world in various ways. I enjoy questions and back talk, and we can do that informally. I will repeat for Zoom people so we don't have to do the mic if you want to ask a question while we're going. Okay, so my goal is to understand the computational mechanisms that you would really need to make a general purpose intelligent robot. And so, what is it that enables you to be, I would say, a general purpose intelligent being? How could I make a robot be like that? And an example problem, just to be concrete, that I actually assigned students in a seminar was to go and make tea in somebody else's kitchen without asking any questions. So I would like to make a robot that could do that. I mean, we should be able to do a lot of other things, but think about the generality of understanding of the world, the dexterity, everything that you need, right? You need to figure out how to make the water hot, where to get the water, what you put it into, where do they keep the tea type stuff. So let's think about how it is that we can make a robot that can make tea in anybody's kitchen. So, I think it would have to be flexible and robust, adaptable, has to have a purpose, it has to be able to reason over a fairly long horizon, a lot of properties that you would want such a system to have. Okay. So let's try to kind of back up and be a little bit formal about how we would want to frame this question. So the way I want to think about it is that we are the robot factory. We're not a factory with robots in it. We're a factory that makes robots. And let's ignore for right now the hardware. Hardware is very important, but I'm just going to focus on software. So here we are, and we have to make robots, and we have to put a program in the head of the robots that we put out into the world. So we'll call that pi. And the question is, what program should we put in the head of the robots? And so one way to think about it is to say, well, there's a distribution over possible worlds that these robots will have to go to. And for some customers, the distribution might be very narrow, right? It might be just, oh, you have to spot weld this one thing as it comes by on the line. For other customers, the distribution might be go to anybody's house and make tea. And so I think the problem of the designer of a robot, in a way, is to say, well, okay, given the distribution over the worlds that it's supposed to work in, what program should I put in its head? Okay. And the reason that I take time to do this is because I think it helps us avoid some set of arguments, right? So somebody might say, oh yeah, and totally it should have learning in it, or it should have symbolic this, or it can't operate unless it has something. But really, if you have a spec like this, and of course it's hard to get the spec, but if you had a spec like this, there would be an optimal program to put in the robot's head, and it would learn if it needed to learn, and it would do symbols if it needed to do symbols. Like, we don't have to care in a certain kind of way. Okay. But it's hard to find, right? So our job as the robot factory, as the people who make the robot, is to consume a spec for what these robots are supposed to do and come up with the program that goes in the robot's head. That's what we all spend all of our time trying to do, except if people do hardware. And that's awesome, but we're not going to talk about that. So the question is, how do we figure out, how do we find the program that's supposed to go in the robot's head? So this is the problem that I want to think about. Okay, so how can we make a general purpose robot? How do we think about this? Well, the one strategy could be to reverse engineer humans. Humans can do these things. Maybe if you figured that out, we could just put that in the robot's head. Another strategy is to do a lot of learning or search or something inside the factory to try to kind of, I think of it as kind of informally as replicating evolution. Another strategy is to kind of do the good old-fashioned thing, which is understand the system and build some controllers and put that in the robot. I would argue that right at the moment, we have almost a monoculture, right? Almost everyone is doing offline learning. Oh, that term means something very specific, and I don't mean it. I just mean learning in the factory, not in the robot, and trying to use that as the strategy, right? So learning in the factory, let's talk about that for a minute. So how do you, what is learning in the factory? I think of this as a romantic strategy, capital R romantic. So what do? We build a distribution of simulators that represent all the domains that the robot's going to have to operate in. We build a distribution of the objectives and the desires and the people that it's going to have to interact with and all this stuff. We make a very general purpose machine learning substrate. We couple these things together in a very, very, very large instance, and we train it until it achieves general intelligence and profit. Okay, so it's plausible in a kind of way, but I think, really only in principle, and I am way too impatient to wait for that process to get to where it's going to go. So I'm going to talk about an alternative strategy. Oh yeah, this is my colleague Tomas. This is a line of his. I just love it. I have to keep it. He thinks, general reinforcement learning, you can think of it as I think it's best understood maybe as a general purpose method for making special purpose machines, right? So RL is a general purpose method. Inside the factory, you can do RL and you can make a machine that goes out in the world and does stuff. And in principle, it could be a way to build general purpose machines, but I think, again, I don't think that can be the whole answer. So the bet that we're taking is that we can actually learn something from humans, from understanding their kinds of modularity, the corners they cut, the things that they do. We can use machine learning techniques, and we can use classical engineering techniques and put them together and get somewhere. And I guess our intuition is that we're going to get somewhere, maybe up the curve a little faster, although those of you who have read Rich Sutton's bitter lesson may have absorbed the message, and he's right in principle, that if you build something into your system, then you risk it being wrong. It'll be wrong. If you build something into your system, it will be wrong. It won't be the best thing you could have built in, but it might be pretty good. It might be enough to get you on the blue curve. If you start with no bias, if you start just having to involve intelligence from the beginning, maybe you're on the green curve and it takes a while to get there. And then there's a question of when they cross, and I have no idea. But I'm going to talk about the blue curve. And so in order to be the blue curve, though, we have to build robots that start out smart at some level and then learn efficiently, right? Because we can't have them taking a long time to learn, especially like in my kitchen. Okay, so how do we get aggressive generalization, right? So this is what we need. We need aggressive generalization. And the only way I really know is compositionality. if you can learn little pieces from small amounts of data, relatively small amounts of data from each piece, and then put them together in novel ways to solve new problems, then you get enormous leverage. And I think that's what we have to do. And we have to find all the ways that we can to really make that happen, right? So this is von Humboldt called this making infinite use of finite means, or making the combinatorial explosion work for us. So one way to think about this is to think about building rational agents, building systems that actually think about what they want. And the reason to build systems that kind of have rationality at the foundation, that understand what they're trying to achieve and reason about the current state of the world and then what actions they should take in order to achieve it, is that it gives us a lot of opportunities for building compositional systems. I should say that I have like a vast amount of stuff that I want to tell you about and not enough time. And so I'm going to zoom in places, but you can ask later if you want to about stuff. Okay. So what I want to do is organize the rest of the talk, with a very old school picture. So this is a picture, I don't know, you could have seen this picture in any paper since about 1975, roughly, about a kind of a high level robot. The details, oh, maybe it wouldn't have said LLM in it, but roughly it would have been the same. External knowledge base, it would have said KB, right? Okay, KB stands for knowledge base for you young people in the room. But one thing that's different, maybe from 1975, is that there's a bunch of boxes that are like mostly learned. I think the yellow things are maybe mostly learned. And there's some other boxes where I think what I want to do is build in an algorithm. I want to build in some systematic reasoning engine that's pretty simple, and then learn the models that they operate on. So there's a lot more learning in this picture maybe than there used to be. Okay. So there's a ton of work on vision algorithms, representing space, low-level reinforcement learning for skills. So people are doing that now, a lot of it, and it's good. And I am not going to talk about it. I'm just going to use it when I need it. Okay, so I'm going to talk about some other stuff. I'm going to start by talking about planning. So that's one of the boxes here. So planning, right? The idea about planning is that instead of just having a policy where if you think of something, you have to do it, right? Planning means trying courses of action in your head and seeing if they're good or not. And that lets you, not have pre-compiled a reaction for every situation. And it gives you, I think, a good, bigger measure of robustness. So we're going to think about systems that reason. And just to kind of start the conversation about how do we do planning, because a lot of people who have thought about planning, they know two cases. There's like completely symbolic state space search, which seems completely inadequate, which is true. And there's like robot motion planning, which is good, but again, just addresses a piece of the problem. So that's also not in itself adequate. And the question is, how do we put things together, and how do we apply planning to more complicated problems than you might initially imagine that we could do? So that's going to be my theme here for a while. So one way to do this is the idea of multimodal motion planning. And actually, I am not going to talk about these words. I am just going to show you a picture. So the idea in multimodal motion planning is a way to think about a hybrid control system, right? So one hybrid system is me and this remote. I can be in different modes. A mode is reasonably smooth dynamics of some sort. So when I'm holding onto the remote in this particular grasp and I move my limbs, the world changes in a certain kind of way. When I put the remote down and move my limbs, the world changes in a different kind of way. And so I make discrete choices about a smooth manifold, right? I move from one smooth manifold to another one by doing mode changes. So picking things up, putting them down, kicking things, just operating in the world in a way that switching the way your dynamics, the way your kind of motor commands affect the world is changing modes. So there's lovely math and so on. And it gives us a structure for thinking about how to do planning in domains where a robot, for instance, has to manipulate objects in the world. And it gives us a kind of an abstraction. And when we think about building abstractions, I think it's important to remember like what makes one abstraction better than another. So kind of like the criteria that I have in mind when I think about building an abstraction is, well, it should make the computational problem easier, right? So maybe I don't reason just at the level of torques now, maybe I reason at the level of these mode switches, it doesn't make your solution quality too much worse. It might be that because I adopt this abstraction, there's some super cute tricks I can't quite articulate anymore, but I give that up. And then, I want it to be not too hard to kind of manage and solve most of my problems. So one little anecdote about this multimodal motion planning idea is that now you can kind of reify that in it as TAMP, as task and motion planning. And so in a task and motion planning framework, we implemented some mode families, right? So there's moving in free space, there's pushing things, there's grabbing something and moving it around, there's operating a 1 degree of freedom mechanism. So those are all families of mode switches and traversals. And it was really easy to implement in a planner. So there's this benchmark called MetaWorld, which was made for doing transfer learning and reinforcement learning. But Tomas and I looked at it and we said, man, we could just plan all those things. So we wrote these operators and called the planner. And so we can, just without any learning, just because we understand physics and geometry, no, really geometry, we can solve almost all these problems. We can solve all of them, right? So some of them involved an interesting kind of frictional operation where the robot would like rub something upward. And so we didn't have a mode description for that. And there was a kind of a tight insertion. But the thing that's interesting is that just without any learning, we got some almost instant leverage on this problem. And other people in our group have applied this in different ways. So Rachel Holiday has been working on reasoning about applying force to objects, and you can use the same kind of multimodal motion planning ideas for thinking about like how to open. This is a child-proof, possibly professor-proof cap. So you have to kind of apply some friction or something to the object before you can undo the cap. So it can think about whether it should go in the vise or on a frictiony mat and so on. You can also do reasoning in belief space. So this multimodal motion planning idea actually applies just as well when the space you're operating in is not the space of world states, but the space of probability distributions over world states. And so this is an example of the robot trying to, believe that the spam is in the bottom drawer. So first it looks in the bottom drawer to see if it's there, because that would be a very efficient way to do it. It doesn't work out. It has to move the spam around and so on. So these ideas of planning in hybrid spaces via multimodal motion planning or TAMP are really quite general. Okay, but then the criticism, so you read papers and then like there's 100 papers now in every conference that say, well, planning would be good, but you have to have perfect models and no one has perfect models, so never mind that, I'm gonna do RL. Right, okay, you have all read one of those papers, probably some of you have written some of them. And so I wanna just start to undermine that a little. Okay. So the first thing is the little project we did, I'd like to call it MOM, for manipulation with 0 models. Okay, well, it's not exactly 0 models. It is 0 models of the objects in advance. So this is, we're gonna have a system that has basically TAMP planning ability, but it doesn't know what kind of objects it's gonna see in advance. It believes that there are rigid objects. And so we use now this is kind of old hat because it's, a year and a half old. So the networks are old, now there are better ones, but we use some neural network to do segmentation and some neural network to predict what would be a good way to grasp an object and another neural network to try to complete the shape, given that we've only seen part of it and so on. And we can name categories, and then we build a policy. Okay, so this is a policy. It doesn't, you might not recognize it as a policy because it's neither a table nor a feed-forward neural network, but it's still a policy in the sense of the IO spec. So images come in, we run all these neural networks in order to build an estimate of what's going on actually in the world. We get a goal from a human in first order logic. Now it can be in language because everything can be. And we call the planner, it generates a plan, we execute the first action, we look to see what happens, and we go again. Oh, earring. Okay, cool. So there's a policy. And I'm just going to show you some examples. This is like the most favorite one, and I want to just show you the setup for a minute. Okay, so the goal the robot had in this case was to put all the objects on the blue mat. Given the robot's point of view, it can only see the cracker box. These are objects, especially that cracker box has been in every robot demo, and everyone recognizes it. It's a YCP object, but I promise you that there is no model in the robot's head of any of these objects. So it looks at the cracker box and it makes a plan. It says, I'm going to put that, all I can see is that cracker box. I'm supposed to put all the objects on the blue mat. I'll put the cracker box on the blue mat. And so it does that. And then, oh no, it looks at the table and it says, oh, actually, there are some other things. So it just calls the planner again, like no big deal, no surprise. Well, it was a surprise, but it coped, and I made a new plan and put the objects back. Okay. So this way, like you get this like beautiful robustness and generality out of this kind of a setup. You know, here it's supposed to put the something yellow on the blue mat. And so it's moving some stuff out of the way. Again, the planner, the TAMP figured out that it had to move those objects out of the way. It tries again when it misses. You sometimes miss too. Here we told it to put every fruit in the bowl of the closest color. It doesn't never seen these fruits, but it can do it. This is another favorite. It was supposed to put all the objects on the blue mat. There was some ambiguity, obviously, about how many among the experimenters too, about how many objects there were. So it will persist and put all the objects on the blue mat eventually. And it can operate on another robot, and it can do other things and so on. So, okay. So the message there is you don't have to know about all the objects in advance. And there's miles to go before that perception is really robust and reliable and clutter and so on. But it's, I think, not a ridiculous approach. So, okay, so we have a planner. We have the ability to cope with perception that's not totally reliable. But maybe, we did program in the basic operations of picking and placing in there, and the planner's model of the mode switches that you get by picking and placing. So what can you do if you don't know everything about how the world works, right? So can we learn some stuff? And so, okay, so lots of people work on planning in some sense, right? In a variety of different kinds of situations. And for any kind of planning, you need some kind of transition model. And the question is, what form should that model take? And so I think it should be easy to learn. It should be easy to learn incrementally. Like you should be able to learn this piece and then that piece and have them not fight with each other. I'll come back to that later. And it should let you reason efficiently once you've got it. And so I think those are sort of the requirements. The immediate caricature of what you should do is you could try to learn mapping from images to images. I think it satisfies approximately none of my criteria, right? Because it's very big, it doesn't generalize very well, etc. So, okay, what can we do? Maybe we learn some latent compressed encoding. I want to skip ahead to a kind of encoding that I think really gives us efficiency in learning and efficiency in reasoning, which is some kind of factored encoding, which can illuminate sparse and local structure in the world, right? So if I do an action, right, like tossing my remote up and down, I am not worried it's going to change the state of the laptop of the guy in the back row, right? I'm pretty sure about there's some locality of effect, pretty sparse, pretty local. The things I do don't change everything. And that is a strong prior. And if you didn't really have that prior, I don't think you could learn anything. I don't think you could learn to be an effective agent in this world. So if we can learn factors that say how some part of the world state depends on some few other parts of the world state when I take an action, then I have a kind of model that is local, can be learned efficiently, and can be used for efficient planning. So I'm going to really focus on this idea of trying to learn transition models that are highly structured. And so one kind of structure is this basic factoring. That's probably pretty clear to everyone, right? The input is a vector, the output is a vector, but we like chunk up the vectors and we say, oh, well, this piece of this vector only depends on these. More generally, we can think about representations that are lifted. That means representations that generalize over objects, right? So I happen to know that, like, if I have something resting on my hand under certain conditions and I move my hand, the thing moves too, right? And I know that in general, it's not about this remote or that water bottle. It's like a kind of a general fact. So the question is, can I build systems that take advantage of that locality and sparsity, but also can generalize over individual objects? So if I can interpret the scene around me in terms of objects, I can think of the objects as indices into the factors. Okay, so let me just do this a little bit slowly, right? So if we just think about the properties of objects, maybe every object has a mass and a color and a name, then I could represent my world state as a set of factors, one for each object. And those factors would themselves be factored into like name and mass and color and so on. So I could organize my representation that way. That might not be rich enough, though. I might be interested in the relations among objects. And so I can also sort of have additional factors in my representation for the relationships among objects, and they could be binary or ternary or whatever. So the idea of objects as indices into a factored representation, I think, is very important, and it gives us a ton of leverage for learning and for planning. Okay, and then I can write, I can start to write rules that look like this, right? So if I have this representation, imagine I want to say if A contains B and B is kind of light, then if I move A some distance, well, the relative pose of A and B, however I move them, and whatever they were before, and the distance I moved will govern somehow, according to some function f that maybe I'm not completely sure about, will govern the pose of B. So you could imagine a rule of that form, which seems kind of tragically ancient and good old-fashioned AI-ish, but it could be absolutely instantiated in a neural network, right? I can have a little piece of neural network that takes some features of some objects and predicts the value of the next one. And it could be that same network could be applied, excuse me. Okay, that same network could be applied in all the ways, in all the combinatorial ways in my world that I could, all these different objects that I could operate on and do things to. So this is a worldview that's actually quite related to the idea of graph neural networks, but it really helps, I think about factored transition models, which is what I think we need to think about for complicated robots. Okay, so one piece of concrete, we have a couple of different strategies for learning these things. I'm going to talk about one of them. Okay, having gone backwards, I can't go forwards. Uh-oh, I have the spinning beach ball. That makes me nervous. Oh no. Okay. Sorry. Okay, that's even weirder. So I think PowerPoint is dying, but it doesn't know it. I might have to like reboot the machine. It is really tragically not responsive. Yeah, I will do that. What's weird is that it hasn't crashed completely, but PowerPoint won't let go. All right, I'm gonna just reboot. Sorry. And I'm sure I've stirred up some questions. Let me just get it going.
What we'll do is we'll, as the computer's rapidly moving, it's
weird because that's still up there, but now I have a black screen here. Okay, we're booting. Okay, good. Ask me questions while we boot and we'll get going quickly again.
Yeah, so I have a question about the factors of objects. So every single factor here seems pretty specific, right? So does thinking about factors limit the generality of this approach? And how do you really take into account all kinds of factors that you would potentially have to handle with?
Right. So when I talk about it this way, it feels like, oh, I, the designer, have to design the factors like weight and mass and whatever. But you could totally use your favorite latent learning, disentangled encoding finder neural network foo to do that job. So no problem. The structural idea is the same, whether a network comes up with the factors or I do. Yeah. Yeah. Yep. Oh, and I will repeat.
But just because we can learn these factors, I would say that organizing the representation of a scene is finding these correct factors, right? You're taking sets of objects in the scene and then deciding how they move with respect to each other and how and there is a granularity at which you would have to build this representation.
Yeah.
So I don't know whether writing down the notion that these objects transform in related ways actually solves the question of how they transform.
It does not solve the problem of learning exactly how they transform, but I think it solves the problem of having a very strong inductive bias that, good, we're almost ready. I have PowerPoint up again. It's meant to be a strong inductive bias. It's meant to be a structural prior that would allow you to learn, but learn in a way that gives you a sparse model. So the critical thing is the sparsity. And so sparsity and generalization, right? So that I can learn these rules now that say for all X and Y, for all objects X and Y, if they have this property or this relation, which I don't know, I'm going to learn that from perception or experience or whatever, but if they have some relationship to each other, and I apply some operator to Y, then they will together have some new property after that. But the point is that it's abstracted over individuals. It's not about that microphone or my remote. It's about objects with certain properties. So this is a structural bias that helps you build systems that then they're efficient to learn and they're efficient to plan with. Okay, I am almost ready. I just have to rejoin Zoom. Maybe someone can tell me the meeting number. Is that possible? Or I can go back into my email. So if you can just read me the number from Zoom. It's up in that little green shield. Okay, I can go find it. Okay, 918
1796
1796
855. Recording in progress.
Okay.
Okay.
Okay. Let's see. I am not a co-host yet. Let's do another question while I'm being made co-host. Yeah.
So it seems really hard to train the way you're describing it.
And, you know, if you wanted to achieve generality at the same time, like you'd somehow need to structure the data collection or learn one skill or one observation at a time in a way that doesn't lead to the ternary blocks kind of overwhelming the 2-piece blocks and so on.
Okay, good. Yes and no, I think. Oh, now I have disabled screen sharing. Okay, now I have this. Oh, yay. Okay. Oh, yay. Okay. Where were we? We were here. All right. I hope I don't have poison PowerPoint in some way. So we have a couple strategies for that. You're right. We don't yet have a whole, one whole thing that works completely. But Jaiwan Mao, one student in our group, has a thing called PD Sketch, where you can write down basically a task and motion planning theory, but leave a bunch of stuff undefined. So you can say there's a predicate, but I don't know how it's defined. There's a piece of the transition model, but I don't know how it's defined. There's some other predicate over here. I don't know how it's defined. And then you can do end-to-end backprop training on that to learn perceptual instantiations of the predicates. So I think there's some hope, right? So that's a kind of engineer writes a skeleton of the theory of the transition model, and then we do classical, self-supervised stuff to fill in all the parameters. Yeah. Okay, here we go. So I'm going to zoom now. Haha, and zoom. So, okay, so we can learn, this is a section that says we can learn these models. And so a group of students in my group led by Tom Silver and Rohan Chitnis for now have been working on learning the whole thing, actually. So learning predicates and samplers and operators. So let me tell you just a little bit more about this. So here's the idea. In this case, we assume that we have a low-level simulation. And so there's low-level states X, and we have a simulator F, which takes a low-level action A and tells us what the result of taking that action is. And what we want is a set of predicates, right? So predicates are just classifiers. Don't freak out. They're classifiers on individual objects or pairs of objects or triples of objects or something. Learn a bunch of classifiers such that if you apply all those classifiers to all those objects, it induces an abstract representation of the state. And then we learn a transition model up at the abstract level, right? Which says, given this abstract state, how does it transition to the next abstract state? And we learn these things called samplers, which take abstract actions, which generally don't have any continuous parameters set, like a grasp or a trajectory. And the samplers suggest sort of values for those continuous parameters. So if we can learn this whole contraption, we can plan efficiently in a very low-level world where we would never be able to plan long horizon plans just using the base level actions. And the details of the learning I'm not going to go into, but the operator learning, so the parts that learn the predicates and the transition model at the abstract level, we use methods that are kind of inspired by program induction and some old ideas from inductive logic programming. And for sampler learning, which is the thing that says, oh, I'm going to take this abstract action, but I have to figure out some continuous parameter values to instantiate it in this particular world. We've been learning kind of some explicit distributional models, and lately we've been, like everyone, we've been using diffusion methods. So we end up with a system that looks kind of like this. There's a high-level planner that operates on the discrete abstract theory. It makes a plan at the high level, and it thinks it knows what predicate should be true as a result of each step. And then it does sampling. It calls these generators of continuous parameters to try to find grasps of objects, placements of objects, trajectories for the robot that are legal in the low-level state and that induce the desired transitions in the higher level state. So that's a kind of a quick thing. And so it can learn quickly from a little bit of data. I'm not going to go into this in detail. But what's interesting is that it learns predicates. It discovers abstractions that seem kind of interesting. So this is actually not in a robotic domain, but it's a kind of a version of doing things with tools. And at the lowest level, it's still continuous. And it learns some predicates that help it organize the planning at the high level, which makes it search for plans at the lower level more efficient. Okay, and so then also, right, you can learn, because we're abstracting over objects, we can learn in domains with different objects and fewer objects and transition to, and just take that same theory and directly apply it with no additional learning to domains with different objects and more objects. So that's an important thing. And those students right now are doing stuff on a spot. So we'll have a paper out about that in a little while so that we can actually do it on Spot. Spot comes with these great built-in behaviors, and so we're able to use those and do high-level planning to use its low-level behaviors. Okay, I want to say something about acquiring new skills. So this gets a little bit to Michael's question about, how do you do this learning, right? So, and I think it wants to come incrementally, right? So if you buy a robot from me and it comes to your house, maybe you're super into knitting or soldering or beating eggs, and the robot might not know how to do that when it comes to your house. You would like to be able to teach it. And so an interesting question is, well, how can a robot that's already pretty competent learn a new skill and add it to its repertoire, right? So assume that, again, we have some good reinforcement learning, which can learn the motor skill part, that can learn the egg beating. But you can't just decide to beat eggs. Like, you have to set it up a little bit. There's some preconditions. You have to have the eggs in the bowl, and you have to be holding the whisk and all that. And so the question is, can you take that new little thing you learned and add it to the rest of what you know how to do? And so one way to think about that is learning a kind of a classical AI looking operator, but it's parameterized by a bunch of real parameters that describe the situation. Like some properties, in this case, again, they're kind of hand-built properties, but they don't have to be. But it says, well, there are some features of the objects that will predict whether pouring, in this case, is going to work out or not. And then what I'm going to try to do is learn a constraint, learn a relation on all those continuous values, the shapes and positions of the stuff in the world, so that if those values satisfy the constraint, pouring will work. If I can learn that constraint, then I can take this pouring operation, I can take its preconditions, I can plug it into my theory, and I can use it to do stuff. So I'm just going to speed through this, right? We do this by getting a bunch of examples of pouring. We do Gaussian process regression. We gather data on the actual robot, which is costly in terms of picking up beans. And so we do careful kind of GP exploration stuff so that we don't have to do too many experiments. And what's good is having learned to do, in this case, it was pouring and pushing. We can just put objects on the table. In this case, it knows the object categories, but not how many or where they'll be. And it can be given a goal. And then you just add the new operations in and it just adds them. So all it did was learn the preconditions for pouring and pushing. And then it can use this stuff in conjunction with things it already knows. So that's what's good. There's one nice example coming up next, I think. Oh no, okay, I'm not gonna wait for it. So, okay, so good. So we can learn these things, we can integrate them into our O-level planner. Another thing is, can we be compositional about it? So we showed that we could learn one skill and we could use it in conjunction with our other stuff. But now I want to think about learning more complex skills. And I want you to watch this video very carefully. And tell me what you would learn from this video. Okay, what'd you learn? Okay, probably not torques. I mean, and probably if you're you probably couldn't execute that next. But it was a trick, right? It was a pattern. It was an idea of a thing you could do. And the question is, can we build robots that can learn from tricks or patterns or ideas like that? So this is some work that Jaiwan's been doing. And the idea is, can we give the robot a single demo of something, right? Like in this case, using the hook to grab an object, and then learn from that demonstration. And classically, what people would learn from this demonstration is like some kind of trajectory, which is terrible. Trajectories are terrible because the objects are never going to be in that place again, right? So trajectories are no good. So I don't know, poses and torques, I'm not sure. You could learn something at the level of contact modes, that's better. But you would like to pack it up eventually into an operation, which is like use a stick to hook something. So the question is, can we learn from that one demonstration the idea of like, you know, pushing down on the thing and catching it with our bucket, or the idea of hooking something? And so we have a strategy for learning mechanisms, and you can think of it as a macro, a little program defined in terms of contact modes, right? So the hooking program is like, I'm going to move, I'm going to grab some object, I'm going to make contact between one of its surfaces and the surface of another object, I'm going to move, and then I'm going to let go. Right? So that's a little program with a bunch of variables in it having to do with the particular contacts and the particular trajectories and so on. And so again, I'm not going to go into this in detail, but what we can do is get one demonstration from a human in a simulator, extract the contact mode sequence, and then mess around. So now the robot plays around with different objects and it tries to figure out good samplers, right? Good ways of taking that generic kind of symbolic pattern and instantiating the continuous parameters so that it can do things. And then training a neural net to do that sampling. So here's an example. Yeah, you don't need to see the charts. So, okay, so here's the thing. So you can show it one of those operations. It can learn the sampler part, right? It can learn how to get good continuous parameters by messing around. That's just like the bucket operator, learning the details of how to do that bucket thing. But most importantly to me is we can take these things again and put them into our planner as if they were primitives, right? So here now the robot it learned about using a hook to do stuff. And now with no further learning, it can use planning to take the use a hook to do stuff operator and use it to get the hook to do the thing, right? So that you can do that. But most of your neural networks, I would argue, maybe they can't, right? So here's a goal. The red box is supposed to be on that white thing, which is slanted and not on the table. And so in this case, it is using its hook idea to hook the thing closer. And then it's going to use a different trick that it was also taught with one demonstration to put the hook thing as a blocker so that the object can't slide off the ramp. So it seems kind of smart. I don't know. We have to watch it. I should speed the video up. Okay, well, it's gonna move that hook over so the object can't slide off the ramp. We don't really want to watch that in detail. Okay, and it can do some other cool things like this is if you have a fat robot hand and you can't pick stuff up very well. This is a good trick to learn. It can use some tricks it's learned to do other stuff. This is another good trick if you have a fat hand and you can't pick stuff up. Again, we taught the robot that trick once, and now it can apply it to different objects in different situations. Yeah, that was a good one too. And you can do it using perception similar to the perception in MOM that I showed you before. It can look at a scene and see these objects and figure out that it could use the banana as a hook for a tennis ball, which is a very important thing to know how to do. And this is a similar thing where it can push the bowl to the side of its little table and grab it. Okay, so just to address a little bit again, Michael was great. He kind of brought up this question. We don't yet have this all into one like singing and dancing system, but another aspect that's really important is being able to learn online as you behave in the world, right? So again, if I send the robot to your house, it's going to see a distribution of problems, and there's no way I can prepare it completely in the factory for your house because your house is different than my house. So it's going to be faced with some distribution of situations, and it's going to have to learn to deal with them. And so it's going to have to do lifelong learning. So Jorge Mendez, who's one of yours and who is now a postdoc of mine, who's been working on lifelong learning, in particular to improve samplers. Right? They play a really important role for us, right? They play the critical role of saying, I have an abstract action I want to execute, like pick up an object. But what are the continuous parameters I should use in this current situation to do that? How should I grasp it? What trajectory should I move it through? So he's working on sampler learning, but in the lifelong learning context. And so this is a kind of a problem behavior. It's a set of simulated domain problems that we've been playing with, because it's hard to get your actual robot to be in a whole lot of really different situations. And so, you might imagine the robot has to do some job like, I don't know, ironing, and it learns what to do, and now it has to do something at a table. And the risk is, right, if you apply kind of standard machine learning methods at the moment, it's a mess, because usually the new thing you do overwrites the old thing, or it messes it up in some way. And then when you go back to the old thing, you're not very good at it anymore. But like when you learn calculus, you don't forget, I don't know, whatever you used to know. So the hope is that things don't, maybe there's a little interference in human learning, but not a ton. In robots, it's terrible, right? So the question is, how do you learn? How can you manage learning when you're in a world where the distribution is changing all the time? And so there's a kind of a classical train test strategy that we're all used to. But really, the way we want to think about it is, no, the robot is moving through the world, and there's some distribution of tasks that it encounters as it goes. And it needs to be able to learn modular subparts for the different tasks as they come by. And so, because the way it thinks about putting things on a table, or the way it thinks about grabbing a table, is going to be different from the way it thinks about grabbing a chair, or different from the way it thinks about grabbing the door. And so we also want to work in a low data regime. And so you might say, well, because you could say, well, for each of those problems, I'm just going to learn a separate sampling. And if you had a pile of data, that would be fine. You could use separate samplers for each thing, and that would be best because they would be most specific. But because we don't have a ton of data, we could instead say, no, you know what, I'm going to pool all the data into a big sampler. So whether you should train the samplers individually or whether you should have one big one on the pooled data is not totally clear. And so what we're thinking about here is saying, well, okay, maybe why not both, right? Can we have individual samplers and a mixed sampler and make a kind of mixture model that uses one sometimes and the other one the other times? And this would be kind of obvious and easy to do if neural networks were good at telling you when they did and didn't know what they were doing. But that is still not always true, right? So you could say, oh, door opening sampler, do you know what to do? And if it said, yeah, I totally know what to do, you would do it. Otherwise, you would use the generic thing. But normally, if you ask it if it knows what to do, it's not so good. So the question is, how do we get these mixture weights? How do we decide how much attention to pay to the specific thing versus the general thing? And so this idea that we came up with of learning a proxy, which is kind of cool. So we could say, well, I have my main neural network. That's kind of like the upper part, which is making the predictions I care about. But I could hang on to it also a prediction job that's just a proxy. It's just a thing that it should know. That's kind of a measure of how well it understands this particular environment. And so in this case, we ask it to predict something that's like the distance from where the robot is to an object. So we're asking this neural network to predict a thing that the robot can perceive. So that seems sort of silly. Why would you bother training a neural network to predict something the robot can perceive? And the answer is because if it can make a good prediction about this thing that it can perceive, which it can test right now because it can perceive it, then we trust the rest of the prediction that neural network is making. So that's a way to kind of decide whether this thing knows what it's doing or not. And so that gives us some reasonably good behavior. Currently in this simulation, the robot that everybody uses is this crazy thing which we call Eggman. Eggman isn't a real robot. Anyway, by doing this, it works much more efficiently. And the robot can really learn online from a very changing sequence of tasks and problems. Okay, this is good. I'm going to get rid of Eggman. Okay, so I'm going to just mention two things and then stop. So one thing I haven't talked about, and approximately nobody worries about, and I want to tell everybody that they should worry about, is remembering what's going on in the world, right? So almost everyone right now in robotics, especially learning-based robotics, is looking at a table, right? We're looking at a table, usually from top down, sometimes from a little oblique angle. But, robots, they have to go around and come back and re-register and understand that this is the coffee mug that they just put down and deal with the fact that we like to talk about the roommate process, right? The roommate process is the process that comes and drinks your beer. So the stuff in the fridge might not be where you left it, right? So how can we use learning and modern perception tools to build a kind of filter that's related to what people used to do for tracking radar blips? Anyway, I do not have time to talk about this, but it's an important problem and more people should think about it. Okay, but I have a fast forward. Another thing to worry about, and again, I have a long story about, is how to do really, really big problems if you have a really small brain. So that, I don't know about you, but it applies to many of us. And the way I want to think about this problem actually is, I will go forward one. Rather than trying to make my planning algorithms work on really, really, really big problems, I want to think instead about going through life, mapping this big problem that I have to face into a sequence of small problems that fit in my small brain, through temporal hierarchy, through abstraction, through organizing, ignoring objects, and so on. So that's another theme. And then the last theme, right, of course, is what do you do about LLMs? What are they good for? And I have a kind of story about that. I don't think I have any great insight, but the way we're thinking about LLMs as a kind of search guidance, right? So for our problems, it's the space of things you could do is very, very big. And having someone suggest to you things is good. It's helpful. It cuts down the space that you have to search. But if you suggested to me that I do something right now, I would not do it uncritically. right? I would try my own personal model of how the world works and see if it seems like a good idea. And so the way we're mostly thinking about using LLMs in the context of this whole thing is as search guidance that we use, but validate or verify using our forward predictive models that we've learned in some other way. Okay, I did not mean to do that. So now I will just skip. Okay, so end of story is really, I think human-like generalization ability stems from learning world models that are combinatorial and efficiently reusable via some built-in architectural constraints. So factored representations, lifted and factored action representations. And we get efficiency in reasoning by exploiting the sparsity of the models that we're learning, and maybe by using these metacognitive abstractions that can take the big problem and turn them into a smaller problem for solving. So this work is joint with students and colleagues. I actually have 4 students on the academic job market this year, and they're all awesome. And so if people want to know about that, I can tell you more about them. And with that, I will let you watch robot outtakes, and thank you for your attention.
All right, we're open for question and answers.
Hi, thank you for the talk. So I have a more like a philosophical question that takes us back all the way to the title. So the title is doing for our robots what nature did for us, right? And from the complex system, perspective, we are the result of emergence from the nature. So we're a complex system. It's not deliberate, but rather we are who we are by necessity, right? But here, the way we are approaching things is more like purpose. It's very purposed, right? So that process is very different. So when you say the title is doing for our robot what nature did for us, what do you really mean? What did nature do for us? And so is it more about the what, or is it more about the how?
It's more about the what than the how. It's all about the what. And what did nature do for you? Well, when you were born, you had an enormous amount of innate structure and reflexes and perceptual wiring and modularity in your brain that made it so that you can learn from like a reasonable amount of data in the wild, right, in your life. And so we have to make robots that are born out of the factory with leverage like you were born with, so that they can learn from a reasonable amount of data. That's the analogy.
Hey, Leslie, I have a question. So I was wondering about your perspective on, the symbolic grounding issue, or how do you ground the task in the, whatever language you come up with. So an example is your paper on learning tasks from one demonstration. Like, how do we know that's a demonstration for, using the hook to like pull the, cube closer to you, and not just a demonstration of, perform the exact sequence of state and action, right? So it seems that the human designer needs to come in and ground, okay, this is a space of tasks as possible. And once you have done that grounding, like, maybe the user specification for that demonstration is actually just having the robot repeat the exact same sequence of motion, and then you wouldn't be able to solve that task, right?
Right, good. So there's some structural assumptions, definitely. So one of the inputs that goes into that system is the goal. And the goal is articulated using at least some vocabulary, which we assume that the system already knows, right? So in the hook using case, the goal was holding. So the assumption is, before we try to teach the robot this new trick, it already knows what it means to be holding an object. Now, we can teach holding before, but once you know holding, that's the goal. The goal is holding. And so, and the assumption is, so what happens is it gets this one demonstration, it knows the goal is holding, it learns the contact sequence, the contact mode sequence. Then it gets a bunch of randomized scenarios on the table in front of it. And it knows it's supposed to be holding the red block, and it has to try to use that trick to figure out how to hold the red block. And so because all these scenarios are so different, that trajectory won't replay. I guess if the trajectory, if I haven't thought about it, I don't know. I mean, if we just gave it 100,000 instances of that same table, maybe it would just learn that trajectory. but that's just so uninteresting that we didn't try it, I guess.
Thank you for the talk. So one question I had was when you were talking about learning abstractions for planning at higher levels, you said something along the lines of it has to satisfy constraints of, for example, dynamic feasibility or something about the continuous representation in the lower skill. Can you talk a little bit more about how that is ensured or guaranteed?
So, and it's interesting because in our group, we have like 4 different task and motion planners and we all do it somewhat differently, but I'll tell you the one that maps nicely onto that. So the idea is you have a bunch of predicates which are defined as classifiers on the objects, on the state of the objects in the world. So and you have a planning theory at the high level. So you call some high level PDDL planner to make a plan. It makes a plan. Now, that theory that it has at the abstract level is not correct. Right? It leaves out details. And so it's entirely possible that the high level planner will say, do these steps and it'll be great. And then now we have to take that high level plan and try to materialize it at the lower level. And that's what these samplers are for. And so the samplers, they say, oh, you want to pick up an object? Well, you need a grasp and a trajectory. And so they're generative models that try to find grasps and trajectories. And so now we do like a backtracking. In one case, we do a backtracking search using those samplers to try to find the details. And then if it tries a certain amount of time, of course, you can never prove that it was impossible. So it tries for a while to materialize this plan. If it doesn't work out, then it goes upstairs and asks the high level guy for a new plan. It says, that didn't work.
Okay, so if I understand it correctly, it sort of checks or verifies if it's feasible and then replans in case. Okay.
That's right.
Thanks.
Yeah.
Thanks.
Uh-oh, there's going to be a battle over here.
I'll pass it to you right after. So thank you, Leslie, for the talk. I wanted to ask about kind of a high level statement that you made at the beginning about this kind of dichotomy between learning with priors and learning without priors, and you showed how these 2 curves cross over, right? But really, it doesn't have to be one or the other, right? And people have thought about how you kind of relax your priors over time and so on. Have you thought about how that fits into the frameworks you're thinking about?
Yeah, no, that's great. And in fact, sometimes I have a version of that with like an upper envelope. So, right. So anyone who sees 2 curves like that would say, oh yeah, really, I want the best of both. And I think like one example of a place where this can happen for us is like things like learning better samplers, right? So you could start out saying, oh, I have a very kind of stereotypical way of doing this thing, but I think using methods a little bit like that mechanism learning, you could imagine taking that mechanism, maybe the hooking thing, thinking of it as 4 steps is not very good, and we should just learn a policy for the whole thing. And so, but what's good is that's a moment where an RL problem now is posed. And you could say, if I've used this mechanism more than a certain amount, I'm going to start caching the values. And so I don't have to keep calling the samplers anymore. And now I'm super good at the hook. And so I think that that's a really important idea, right? Because right now, we don't have a good way to frame sub-problems no one roughly knows how to frame a new learning problem kind of organically online, right? They're kind of like, oh, I have to learn to do this now. And so that might be a way where you start doing it very deliberatively and you gradually compile the frequent parts into very fast stuff. Yeah.
Thank you.
Yeah.
Hi, Leslie. Very refreshing talk, although it is foundational material. The example with the bulldozer was very intriguing, but I missed how the robot will predict what will happen if the robot will push the rock like backwards, right? The physics of it. Is it something that will be learned, or is it something that will be somehow encoded there the same way you encode higher level stuff?
Yeah.
So the question is a little more general. At which level you use symbols, right? I mean, do you use symbols at the physics level or only at the compositional level?
Right. That work presumed that we had an accurate physics simulator. So that when we drop a rock on one side of the plate, the other thing will flip up. And we have not worked on trying to learn the physics simulator, which in the end you probably have to do. But that seems not easy, but maybe sort of not impossible.
But this is only the difference between mental and executing physical, right? That's if I had a model, like Michael Polla has, for example, for contact, I would just apply the equations of the torques there, and I would be able to predict.
I see.
I would know the x
Yes.
one is equal to f of x.
Yes. But what we're addressing is the search problem. So we're assuming that there is a low-level model, and if a brilliant person can derive the but it's hard. It's the phenomenon we're trying to get at is that there are search tricks, that there are kind of shortcuts in search space. And that's what you learn when you see something like that. Like, oh, I could do it that way. So that's like it's like, I don't know how to really explain, right? So it's not learning the model. We're not about learning the model. Here we're assuming we have it, the forward model, but we're assuming we have the forward model at a very low level. And that if we planned at that low level, we would be sunk. And so this is just an idea about how to plan efficiently. But yeah.
One more question. So you talked about the metacognitive ability, that is knowing what we don't know and then incorporating for what we don't know. The representations, the sparsity and the abstractions that you talked about before, do you see that actually help in detecting or knowing what we don't know?
Yeah, good. So the metacognitive thing actually was not so much about the knowing what we don't know, but rather the following problem. The following problem is I have my overall problem, which is my life. And then I have to like get myself to this auditorium today. And so how do I take my whole problem, which is, I don't know, to lead a purposeful and happy life or something, and turn it into which way should I walk in order to get here? And so I can think about, so I want to say, I'm going to map the big problem into a small one. And I'm going to map the big problem into a small one by doing hierarchical temporal decomposition, by caching certain decisions, like to be a professor, to come to give this talk, those things. So I'm going to kind of manage my intentional state in a way that makes it so that I only have to solve small decision problems. I only have to plan how to walk here from the hotel, or maybe I had to plan at an abstract level a while ago, whether to take the train or not. And I had to plan it. So, but when I frame a new problem, I can ignore most of the dimensions of the state space. I can ignore most of the objects in the world. I can ignore most of the times and just give myself a little problem. So that's what that's about. Yeah. Thank you.
Thank you very much, Leslie, for that
Sure.
really stimulating talk. Please come next Friday. We'll have Professor Nick Gravish speaking from UCSD. If you want more information about upcoming events, check us out on social media or check the website. Thank you so much, everyone, for coming. And thank you so much, Leslie, for the very, very exciting talk.